Hello dear students, welcome to another session on NMR spectroscopy. In the previous session, we were talking about the basic concepts in NMR spectroscopy and the different steps involved in signal generation. We have not yet reached to the signal. We are still in the process of signal making. So let's see what we have today. But before that, let's have a recap of what we discussed last time. So we discussed different steps, starting with the placement of an NMR active nucleus inside a magnetic field. So when you put a nucleus inside the magnetic field, there are two things that happen. First, it starts precessing with a particular frequency that we call the Larmor frequency, and it arranges itself in all possible spin states. So these nuclei, they arrange themselves in all possible spin states depending upon the spin quantum number. So for a spin half nucleus like proton and carbon-13, there are two possible spin states, one that is aligned along the direction of the applied magnetic field and the other that is aligned against the direction of the applied magnetic field. Then we discussed that there is a slight axis of nuclei in the lower energy state, and the magnetic moments or the magnetizations of the vectors in the alpha and beta states, they cancel each other. But because there is a slight axis in the alpha state or the lower energy state, there is a net magnetization that is left behind. And these are the nuclei that are in the alpha state or aligned along the direction of the applied magnetic field. They are combinedly written or drawn as a bold vector, which we call the net magnetization vector. And this net magnetization vector allows us to see the system as a whole. Now, this magnetization vector on the XYZ axis is shown pointing in the direction of Z axis, which by default is written as being in the direction of the applied magnetic field. And then we have the x-axis and the y-axis on the horizontal plane. Z-axis is on the vertical plane. Now, the next step is to provide it energy. So when we provide energy, these nuclei, they absorb some energy or some frequency from the radio frequency transmitter, and they move from alpha to beta state, or they jump from alpha to beta state. Now, the energy that is absorbed by these nuclei is exactly equal to the energy difference between the two states, that is the alpha and beta states. So energy is transferred in the form of radio frequency. Each of these nuclei, depending upon their shielding or de-shielding or the induced magnetic field or the overall, the net B effective that they receive, they will absorb energy. All right, so they do not experience B naught exactly because of certain shielding and de-shielding effects because of its surrounding atoms, and that is why the Larmor frequencies or the resonance frequencies of these nuclei may be different within a molecule. The next question is, how do we transfer this energy? And that is what we are going to discuss today, and later we will end up this session by having the finalized NMR signal. So let's begin our today's topic. That is the transfer of energy. So how is this radio frequency or the energy transferred from the radio frequency transmitter to the nuclei under study? So there are two methods to provide this energy or transfer this energy. One is the continuous wave method and the other is the pulse NMR technology. Continuous wave technology is the old-fashioned technology used in the older NMR instruments, while pulse NMR technology or pulse Fourier transform NMR technology is used in the modern instruments. So in the previously used instruments, a continuous wave of fixed radio frequency was used to be transferred to these nuclei or provided to these nuclei, and during this experiment or during this process, the field would be swept from low to high field. What it means is that people used to provide a fixed radio frequency by keeping on the radio frequency transmitter continuously and sweeping the magnetic field or changing the magnetic field from low field to high field. That is why it's known as a continuous wave NMR technology or NMR spectrophotometer. The resultant is a frequency domain spectrum in which every different type of nucleus means, or every different type of proton means, those protons having different Larmor frequencies or resonance frequencies. They are excited one at a time. So as the field increases from low to high, the Larmor frequencies increase, and because you have kept this radio frequency transmitter at a fixed frequency, as the magnetic field increases, the Larmor frequency increases, and as soon as the Larmor frequency reaches or it matches the radio frequency coming out of the radio frequency transmitter, the nucleus or the proton flips. And then, because the Larmor frequencies of all the protons are increasing, because we are constantly increasing the magnetic field, then the frequency of another, the Larmor frequency of another proton reaches this level, and then it flips, and then another one. And so all of these nuclei, they are made to flip or absorb energy one at a time. It takes some time. And that is why it's a slow process. But in the modern pulsed Fourier transform NMR instruments, we provide a strong but short burst of radio frequency, keeping magnetic field fixed. So in the modern instruments, usually a superconducting magnet is used. In the previously used instruments, electromagnets were used, but in this method, in the pulsed Fourier transform technology, superconducting magnets are used to provide a strong homogeneous magnetic field, and a short burst of radio frequency is transferred to the protons. Now this short burst is provided at the frequency, at the resonance frequency or the Larmor frequency of the protons. We already know from that table that if you have a particular magnetic field, you can actually tell what would be the Larmor frequency of these protons. And so this pulse is provided at the frequency of those protons, and that is why they flip. All of them flip at once simultaneously, and then they are recorded by the recorder, and we get a signal. So we will be focusing on pulsed Fourier transform technology because that is in use nowadays. So pulse really means turning on the radio frequency transmitter for a very short period of time and then switching it off. It's like a pulse, it's like your pulse actually, that turns on and off for a very short period of time, but it's a very strong pulse. Now, giving one pulse is one experiment, one NMR experiment. Then giving another is another NMR experiment. And that is why, because of this technology, several NMR spectra can be obtained in a very short period of time. I told you in the continuous wave technology, all of these protons, they are made to excite one at a time, and it takes some time to record one spectrum. But in pulse NMR spectroscopy, you can record a lot of spectra in a very short period of time. And that is why, because you have the luxury of obtaining these spectra in a very short time, you can actually record a lot of spectra and then stack them together to get a good signal to noise ratio. A good signal to noise ratio means a strong signal with lower noise. You would like to have clear, strong signals with lower noise level. So the advantage of pulse Fourier transform technology or the previously used continuous wave technology is that it's faster and the signal to noise ratio is very good. Means you can get a very good spectrum in a very short period of time. So what happens in the pulse Fourier transform technology is that all of the protons, as I told you earlier, are excited simultaneously, and then they are allowed to relax back. This is a very important step or important part of the signal generation in NMR spectroscopy, and that is relaxation. You have excited the protons, you have provided energy to the protons, but unless and until you allow them to relax back, they will not give you a signal. If you remember, I told you about saturation in the previous session. Saturation means when you do not allow these nuclei to relax back to z-axis. Like magnetization, the net magnetization vector has its equilibrium position on z-axis, on the vertical axis. When you provide it energy, it flips. But if you do not allow it to go back to z-axis, it will remain on this xy plane and it will not give you a signal. And that is a state when saturation happens, when you continuously provide it energy and do not allow it to relax back. But in a pulse technology, because you're turning on the radio frequency transmitter for a very short period of time, it excites the protons, and then when you turn it off, it allows them to relax. And there is a slight delay between two pulses or two experiments, and that is known as the relaxation delay. So you allow all the protons to go back to z-axis, and then you give another pulse and excite them again. Relaxation happens by two mechanisms. One is known as T1, the other is known as T2. T1 is the time taken by the nuclei to relax, and same is the case in T2. We will not go into the details of relaxation methods, but there are two methods, that is the spin lattice relaxation and spin relaxation. In spin lattice relaxation, these nuclei, they dissipate their energy to the surroundings and relaxing back towards z-axis. In spin relaxation, one spin means the nucleus. One nucleus provides its energy to another nucleus, and so it relaxes, exciting the second nucleus. So in spin lattice relaxation, energy is released in the form of heat to the surrounding, and in spin relaxation, it is transferred actually from one nucleus to another. So we're not going into details of that, and the time taken by the nuclei to relax back through these two methods is known as T1 and T2. You can actually calculate the relaxation times for different nuclei. So relaxation is very important, and it is actually during relaxation that the detector sees your net magnetization vector or your nuclei when they go back towards z-axis, and that is when it records a signal. So this whole process, this whole experiment, which involves three things: the pulse, transfer of energy, the FID, which I will tell you in a moment what it means, and the FT, the Fourier transform. It takes only a few seconds. So what does these three things mean? Pulse, I told you earlier, is the transfer of energy. When you turn on the radio frequency transmitter for a very short period of time and then turn it off, these nuclei, when they are excited and they come down to the XY plane. And then when you turn off the radio frequency transmitter and allow these nuclei to relax back, that is where the detector sees it. The detector sees M0 going back. And because it's going away from the detector, the signal decays with time. When it is closest to the detector, the signal is of highest intensity, but as soon as it goes back, and it doesn't go back straight, it goes like this around the z-axis and it moves away from the detector towards the z-axis, and that is why you get a decaying signal. That decaying signal is known as the FID, the free induction decay. It's a time domain signal, remember. A time domain signal means that the intensity or the amplitude of this wave that is generated or the signal that is generated is dependent upon time, or it decays with time. That is why it's known as a time domain signal. This FID cannot provide a lot of information to us. We cannot interpret it, and that is why it's necessary to convert this time domain spectrum or signal into a frequency domain spectrum or signal. And for that, we have this mathematical operation, which we call the Fourier transform. So once you have the FID, once you have acquired the FID, it is converted into a frequency domain signal with the help of this mathematical operation, which we call the Fourier transform. And as soon as you apply Fourier transform, you have the signals, you have the spectrum, and then it's ready to be interpreted or read. Now this whole process, the pulse, the FID, and the Fourier transform, it takes only a few seconds. So you have the liberty of recording a lot of spectra in a very short period of time. It takes a few seconds, all of this process, and so you can repeat the process again and again in a very short period of time. And when you repeat it again and again, these signals, these spectra, they are stacked together upon each other, leading to a very intense signal with lower noise levels. Why we get an intense signal when you stack them together is because of the fact that these signals, every time they will appear at the same position, and so the intensity multiplies. But noise is random, and that is why it grows by square root of n. N is the number of scans. So as you increase the number of scans, the noise increases by a factor of square root of n, and that is why you get a very good NMR spectrum. So it's a fast method with low noise, a good NMR spectrum, and that is why it has replaced the continuous wave NMR spectrophotometers. So this is how you transfer the energy. And this is a picture of the modern instrument that we have here in the Institute of Chemical Sciences, University of Peshawar. You see this cylindrical type of structure. This is actually the magnet, and right in the center you have the input system. So your NMR tube along with your sample goes inside. Here is the probe right in the center and surrounded by the radio frequency coils and the magnet coils, and this magnet is actually immersed in liquid helium. And for that, you see these 4 filling inlets, 2 here in white and 1 here in black, and the other one is right behind this white one. So we have 2 cores. The inner core, these 2 whites, they are for filling liquid helium. So the inner core is filled with helium to keep the superconducting magnet at a very low temperature, to keep it as a superconducting magnet. And the outer core is filled with liquid nitrogen, and that is to keep liquid helium in liquid state, right? So every week you have to refill liquid nitrogen because it's closer to the environment and it evaporates quickly. But liquid helium, because it's inside into the inner core, it takes 6 to 8 months to be refilled, right? And it doesn't have to go below the threshold level because that will quench the magnet. And it is connected to the console, which is then connected to the computer. So signals from this magnet goes into the console, and then they are taken up by the computer. And now, because these pulse Fourier transform technology is connected with computers, so there are softwares that can operate these machines, and you can do everything in an automated fashion. So what is pulse NMR spectroscopy? It's a sequence of pulse that we give in all of these different experiments. As I've told you earlier, that NMR is a very vast technique, and it has a lot of different techniques within this, and all of these techniques, they differ from each other by the sequence of pulses. So the application of these sequence of pulses of different phase angles is the soul of all NMR experiments. We have different experiments, and each of them differs from the other by the sequence, by the pulse sequence. What is the meaning of the phase angle? The angle at which it flips the magnetization vector. So it's at z-axis initially. When you provided the pulse, the energy, it flips. So if it flips by 90 degree, we say that the phase angle is 90 degree, or it's a 90 degree pulse. If it flips by 45 degree, we say it's a 45 degree pulse. If it flips by 180 degree, we say that we have given a 180 degree pulse, or whatever pulse you have given. Now, on what factor does this phase angle is dependent? It's dependent upon the duration of the pulse. So for example, you have given a pulse for a particular time period, and it flips the magnetization vector through 90 degrees, and we say that we have given a 90 degree pulse. We have given a pulse for such a duration that it flips m0 by 90 degrees. But what if you want to flip it through 180 degrees? Then you have to increase the duration of the pulse. So you double the duration of the pulse, and it flips it through 180 degrees, right? This is a simple single pulse sequence. So you see here, it starts from here, you give it the pulse, and then you turn it off here, and you see that this m0, it goes back, going away from the detector. The detector is on the XY plane, So here is the detector, and it goes away from the detector, and that is why you get this decaying signals. And you see that you have this wavy structure. It's a decaying signal, and that is when you are acquiring all the information about the molecule, right? And then you allow it some more time. It goes down here and it almost reaches zero here, but still you allow it some time to relax so that all the protons reach z-axis back, and then you give another pulse. So you give it some relaxation delay, and then you give another pulse, acquire again relaxation delay, then another pulse, and so on. So it's a one-dimensional single pulse sequence. There may be experiments in which you need to provide more than one pulses, but here just a single pulse sequence is shown. This is the FID, this decaying signal, and that is where all the information about the protons or the molecule is recorded. So what are the steps? Let's see. So we have P naught pointing up. You turn on the magnet. All of these nuclei, they start precessing with their Larmor frequencies, arrange themselves in all possible spin states. There is a slight axis of the nuclei in the alpha state that is shown in a combined way as M naught. And your M naught now is on z-axis. So this is your z-axis. Here you have the y-axis, and here you have the x-axis. And now you give it a pulse. And that pulse, you need to know this nomenclature. You give it a 90-degree X pulse. 90-degree X pulse. So the phase angle, I already told you, is actually the duration of the pulse. You give this M naught a pulse for such a duration that it flips it through 90 degrees. And that is the phase angle. So you are actually going to flip this M naught, or you want to flip this M naught through 90 degrees. But what about X? What is X? X is the direction of the pulse. So you are giving a pulse in X-axis for such a duration so that M naught is flipped through 90 degrees. Now, if this is your X-axis, this one, and you are giving your pulse in this direction, where will your M naught go? This can be seen from the left hand rule. So if the thumb of your left hand points in the direction of the pulse, like for example, it's pointing here towards x-axis, then the curved fingers will point in the direction where your M naught will move. So see here in the slide, if this is x-axis and here your thumb is pointing in this direction, then this M naught will flip towards y-axis. So if you are giving a pulse in x-axis, this M naught will flip towards plus y-axis. If you are giving a pulse in plus y-axis like this, then your M naught will flip towards minus y. If you are giving a pulse in minus x-axis, then it will move towards minus y. If you are giving a pulse in minus y-axis, then it will move towards plus x-axis. So that is very important to know where your M naught lies at a particular point during the experiment, and that is why I told you earlier that the position of M naught is very important. But now, because you know that you are giving the pulse in x-axis, it will move towards y-axis, and this is what happens. So here is your x-axis, and you gave it a pulse through 90 degrees, and it has flipped through 90 degrees, and now it lies exactly on the y-axis, right? The pulse has stopped because you give it for a very short period of time, and when you turn off the radio frequency transmitter, it goes back towards z-axis. So it tries to relax back, and this is that relaxation delay. You allow it some time to relax back, and all of these nuclei, they will absorb energy according to their Larmor frequencies. And this is what you get, a decaying signal that varies with time. This is not of much use to us, and so we have to convert it to a frequency domain signal through Fourier transformation. And when you apply that, you get a frequency domain signal, which is the final NMR signal dependent upon frequency. Now, I leave you with a question. we have discussed that not all of the protons might have the same Larmor frequency, and for that matter, not all of the protons in the molecule might have the same resonance frequency. But we just saw in the pulse Fourier transform NMR technology that we are giving a pulse at a fixed frequency. For example, the magnet inside your machine is operating at 7.05 Tesla. What does that mean? If your machine is operating, or your machine has a magnetic field that has a strength equal to 7.05 Tesla, then the resonance frequency of the protons, if they are not under the influence of any external factor, the Larmor frequency would be 300 megahertz. So if the magnetic field strength is 7.05 Tesla, which we have seen in that table which I had showed you earlier, then the Larmor frequency or the resonance frequency has to be 300 megahertz. But we have also seen at the end of the last session that not all of these protons, they would get 7.05 Tesla. Why? Because of shielding and deshielding. So some would get lesser than 7.05 Tesla, others might get more than 7.05 Tesla, and that is why their Larmor frequencies or their resonance frequencies will not be exactly 300 megahertz. But if your machine has a 7.05 Tesla, then the pulse that you will give is at 300 megahertz. Then why all the protons would be excited? Because not all of them would receive 7.05 Tesla and not all of them will have 300 megahertz as the resonance frequency. Then why all of them are excited simultaneously? Can you think about it? Let me tell you. As a matter of fact, when we give a pulse, for example, at 300 megahertz, now this pulse has a frequency of 300 megahertz plus minus a few hertz. It may not be exactly 300, but it may be 300 megahertz plus minus a few hertz. And I have already told you that the induced magnetic field that is generated because of the electron density is a very weak field. So this B naught is shielded by the B induced to a very small extent. And so it diminishes to a very small extent and it lowers the Larmor frequency by a few hertz. So the difference of frequency between all of these different types of protons in a molecule is not in megahertz, but it's in hertz, because the difference of the induced magnetic field between these is not a great deal. And so it changes or it varies the Larmor frequencies of these protons in a few hertz. And luckily, when we provide the frequency at or the pulse at 300 megahertz, it is plus minus a few hertz, and that plus minus a few hertz is enough to cover the whole range of the protons that are present in your molecule. I hope you got the point. And so all of these protons, they extract their required energy or frequency from that range which we have provided, that is 300 plus minus a few hertz, 300 megahertz plus minus a few hertz, and so they extract their own frequencies, and that is why they flip at a time and then they relax back, giving you signals. Now these signals will not be at the same position, they will be at different positions. Why? Because now we have a frequency domain signal, and in a frequency domain signal you will have different positions for these signals. Why? Because all of them have different frequencies, different resonance frequencies or different Larmor frequencies, and that is why on a frequency scale they should appear at a different position. Yes, so we will have more than one signals for all of these different types of protons. If there was no shielding or deshielding effect and the Larmor frequency of all of these protons would have been similar, NMR would have been useless. But luckily they do not have similar Larmor frequencies. and that is why they appear at different positions, and we can analyze them through their frequencies. So this is how a real time domain NMR spectrum or free induction decay looks like. This is the FID of a molecule that I had analyzed myself, and it contains the decaying signals of all the different types of protons that are present in that molecule. So it has mu1, mu2, mu3, mu4, and so on. All of these frequencies are stacked together, and that is why I told you that this time domain signal, which decays with time, is useless to us. We cannot interpret it, we cannot read it, we cannot extract any information from this FID about the structure of the molecule. So what we need to do is to convert it into FID. To convert it into a frequency domain spectrum. So this FID complex signal, which is a mixture of the frequencies. So all of these frequencies are mixed in this one FID. It's a mixture of frequencies that decays with time. So what Fourier transform does is that it separates all of these frequencies. It separates them out and then converts these individual frequencies into a frequency domain spectrum, which we can easily read. Now this is the frequency domain spectrum of this FID. You can see how clear it is, right? So if you see the scale here, it's in seconds, means it's a time domain signal, and here is the intensity, so it decays with time. And here, if you look at this scale, it's in frequency. You can see F1 here. It's written in units of ppm, parts per million, that we will discuss in the next session why it's written as ppm, but it is a frequency domain spectrum, and this is the intensity. And now you can see from this spectrum that we have three signals here, another here, then a big signal here, some smaller signals here, and a small signal here. So they appear at different positions, and each of this different signal corresponds to a different set of protons. So this signal here shows that these protons have a different Larmor frequency from the rest, so they appear here. And then we have these three signals here which appear at different positions. You can see there is a slight difference of frequency between them, and it's completely different on the opposite side from this one. And then we have some signals right in the center, and so all of these different types of signals suggest a particular set of protons having different Larmor frequencies or resonance frequencies. So finally, we have the NMR spectrum. I hope you understand all the steps from the start involved in the NMR signal generation. And finally, we have the frequency domain NMR spectrum. And this is the proton spectrum that we are going to interpret and get information about the structure of the molecule. So thank you so much for watching this one. Stay tuned. We will discuss some more topics in the upcoming lectures. Thank you.